When we look at the sunrise or sunset, the sun appears to be a yellow disk, but actually the sun is more than 333,000 times massive than our Earth and 1,047,000 times massive than Jupiter, and so is the gravitational force of the sun. It is well known that every object in the universe, which has a mass, makes a curve in the spacetime. The bigger the mass, the more curved shape the spacetime will be. But this doesn't affect the speed of light, which always covers the required distance in the same amount of time, even in the curved spacetime, as it would have covered in a straight line. Actually, it is the time which slows down at the massive object. Recently, the solar Parker probe nearly touched the sun when it approached near the sun. But what if some spacecraft succeeds in landing at the surface of the sun in the future? The question is whether there will be any time dilation at the sun. It has already been proved that the time at the surface of Earth is a bit slower than the time in the space itself. This happens due to the gravity of the Earth and absence of gravity in the space. But the gravitational power at the sun is huge. The gravity at the surface of the sun is about 28 times more than the gravity at the surface of the Earth, and the escape velocity of sun is about 55 times more than the Earth. If two clocks are put simultaneously at the surface of the sun and the Earth, with both exactly showing the same time, after a period of 1 year, the clock at the sun will be 1 minute behind the clock at the Earth. This time dilation effect may appear small, but it accumulates over the vast timescales of our solar system. If the sun and the Earth were formed at the same time, due to the weaker gravitational force at the Earth is actually now about 8,000 years older than our sun. The core of the Earth also experiences the effect of the time dilation, making it around 2.5 years younger. These principles apply on smaller scales too. People living at higher altitudes like mountains with slightly weaker gravity age faster than people at sea level. Even within our own bodies, the force of gravity is minutely less at our head compared to our feet, meaning the top of our bodies age faster, though it might be less than the billionth of a second. The same time warping effects that stretch and compress time near Earth also act dramatically on other massive objects in our solar system and universe. The gravitational field on Jupiter is much stronger than Earth's, meaning time passes more slowly there. And as immense mass drags space-time fabric inward, the flow of time slows to a crawl near black holes. At their event horizons, the point of no return, time stands still compared to the rest of the universe. These relativistic time dilation effects are predicted by Einstein's revolutionary theory of general relativity, which models gravity as distortions in the fabric of spacetime caused by mass and energy. Simply put, the greater the warping of spacetime, the slower time passes at that object. Experiments have validated time dilation in a variety of settings, to cosmic ray particles decaying more slowly when approaching Earth. The extreme gravity and concentrations of mass required make directly observing gravitational time dilation tremendously difficult. The recent Parker Solar Probe that skimmed the sun provided a taste, as its onboard clocks will lag ever so slightly behind Earth clocks after flying so close to our star's intense gravitational field. But landing a probe on the surface of the churning solar furnace remains an enormous engineering challenge. Should future spacecraft overcome the scorching temperatures and hazardous environment to land on the sun, they would allow an unprecedented direct measurement of gravitational time dilation. Atomic clocks on the solar surface would tick slower and drift out of sync with Earth clocks. Based on our models, in 1 year on Earth the solar clock would lag by about 1 minute. Extending the comparison over billions of years would reveal drastic time warping effects. Proving Einstein right under the sun's titanic gravity would provide dramatic confirmation of relativistic physics. And comparing solar and terrestrial time could also help answer astrophysical mysteries like reconciling models of the sun's age and evolution. As with so many voyages of discovery, the epic journey to touch our nearest star promises not just scorching adventure, but insights that could reshape our understanding of the universe.